Okay, so I'm back again. I decided to switch over to a different whiteboard here. So we want to continue where we left off with C of 3.51, part C. Now notice that when we were looking at that part A, right, and even part B, we saw that there was a form that our joint probability distribution always had. So let's see if I can write that in the form of it. So the probability that X is equal to X, Y is equal to little y, that is equal to, if we look at that, that's essentially 4 choose X, right? 4 choose Y, and then 4 choose the remaining 3 cards if we of X and Y. So if we chose 0 cards from of X and Y, then we have 3 cards left. If we choose 1 card of each of X and Y, we had 1 card left. So we think about this as just 3 minus X minus Y at the bottom. So subtract away those cards. So we get this is 3 minus X minus Y represents our remainder, divided by 12 choose 3, where X could be from 0 to 3, and likewise Y can be from 0 to 3. And then we see that if X and Y are both above the value of 3, when you add them together, then that probability becomes 0. So 4 choose 3 is a valid number, but when you do 4 choose, and here we get a negative number at the bottom if we have anything that is, so we get a negative number at the bottom here, okay, right here. If we plug in any combination of X and Y, that when you plug it in here makes this negative, so this whole probability will become 0 in that situation. Okay, so that is the joint probability distribution function of X and Y. And now let's continue with our next topic, which is continuous random variable joint distributions. So joint distribution of continuous random variables. Okay, and so for that, we have our joint density function. It has to satisfy 3 conditions as well. F of xy has to be greater than or equal to 0. Okay, and then when we integrate over all my x and y, f of xy, I have dx dy or dy dx. It doesn't really matter which one. It has to be equal to 1. So we're doing a little bit of calculus 3 here. And then the probability, the last one is that the probability that my point xy is in some region A, okay? So think about, you have a xy plane and you have some region A within the xy plane. That's going to be equal to the double integral over that region A, okay? My function f of xy, dx dy or dy dx, it doesn't matter. Yep. So let's look at an example of this. I'm going to example 3.43 on the next slide. And it is, we'll call this the stimulus example. And it says this: let X denote the reaction time in seconds to a certain stimulus, and Y denote the temperature in degrees Fahrenheit at which a certain reaction starts to take place. Suppose that 2 random variables X and Y have a joint density given by f of xy is equal to 4xy. X goes from 0 to 1. And then we have Y also go from 0 to 1. 0 elsewhere, okay? And let me just draw the region, the region of my function here. When it comes down to it, my region is really just this square. Okay. In the XY plane. Okay. This is square. And so A says, what's the probability that X is between 0 and 1/2 and Y is between 1/4 and 1/2? So let's put that here. Probability. X is between 0 and 1/2. And Y is between 1/4 and 1/2. And when you think about this, I'm going to just draw the region here. A. This is my region A. Right, we're looking at the region from 0 to 1/2. Okay, and then from 1/4 to 1/2. Suppose 1/4. This is 1/2. Okay, so we're looking at this region. Okay, so I want to know what's the probability of that region there. And we can find that by integrating. And it doesn't matter which one you put first. You can do dx, dy, or dy, dx. But I have my function 4xy. And I'm going to do dy, dx, because why not? Okay, dy, dx. So y first, y goes from 1/4 to 1/2. Okay, x goes from 0 to 1/2. If you plug that in, you work that out, you get 3/64. Here's my answer. Three over 64. Okay. Okay. So let's look at another problem. Let's look at part B. So what's the probability that X is less than Y? Now, when we deal with this one, we need to figure out where this occurs in our domain. When is X less than Y? So let's draw a domain again. Okay, it's a square. Okay. Okay, so a square in the XY plane. And the best thing to do is when we look at this, we have X less than Y. When we want to graph this X less than Y, we should look at the equality X equal to Y. So let's look at the equality X equal to Y or Y equal to X. And let's draw that on the graph. So let's draw Y equal to X. Here it is right here. Here's Y equal to X. And where is my function? Where is X less than Y, right? Because now we split this. If you look at this, we split this square up into two pieces, right? Something above the line, Y equal to X, and the region below the line, Y equal to X, right? Of these two regions, which one satisfies X less than Y? Well, that's going to be the region above the line. This part right here. Just pick a point, right? Just pick a test point like 1/2 3/4, right? 1/2 3/4 is above the line Y equals X, and it satisfies that inequality that we have. The X is less than Y. Okay. Check that out for yourself if you don't believe it. And now we need to just come up with our equation. Okay. Now let's think about that. The probability that X is less than Y. I have a double region over 4xy, and I can do dy dx or dx dy. I'm going to do dy dx. Now, what's the range of y? Well, y can go between what? Two values. Y can go from align y equal x to our other line, which is y equal 1. So our limits of integration, just remember from calculus 3, it's going to be y equal x to y equal 1. Okay. What does x go between? Well, if you guys remember from calculus 1, then our limits for the x are going to be constant, and they're going to go from 0 to 1. And if we integrate that, we get 1/2. It's a little bit anticlimactic here. Now, don't think that's 1/2 is the answer, because that's the area. We have half of the area of the square here. It's just the probability just turned out to be 1/2 in this instance. That's not always going to be the case. All right. So let's look at another problem. Let's look at another concept, which is called the marginal distribution. So marginal distributions. And if you guys have been noticing with the joint distribution, right, we're dealing with both x and y at the same time. A marginal distribution says, can we distill the probability of x from a joint distribution? Or can we distill the probability of y from a joint distribution? Can we get the probability of x alone or the probability of y alone? And we can, using a marginal distribution. So for the discrete case, we have g of x, the probabilities of just x alone. We're going to sum over all the y of f of xy. And what this literally means is that what we're going to do is we're going to keep x constant. And as we keep x constant, we're going to sum over all the y values for that constant value of x. And we're going to do that for every single value of x. And we can do the same thing for y. And we're going to look at an example of this in just a second. We can sum over all the x, keeping y constant. And we can find the probability of y alone. This can be extended to continuous distributions, where we integrate over all of the y values to get the marginal distribution of x, or we can integrate over all of the x values to get the marginal distribution of y. Okay. Let's look at an example, which is example 3.50. Okay. And I'll give it, I don't know, we'll just call it the marginal example. I don't know. That's some really bad handwriting there. And we have a table. Let me draw a table here. We have x above, we have y there. Okay, it's function f. X goes from 2 to 4, y goes from 1, 3, and 5. Okay, and we have probability 0.1, 0.15. We have 0.2, we have 0.30. We have 0.1, and we have 0.15. Okay, and we want to find the marginal distributions of x and y. And what that literally means is that what we're going to do is we want to, if you guys remember when we did we did an example where we had hypertension, we had smoking and heavy smokers and moderate smokers, right? We had like subtotals on the side. What we're going to do is the same thing, totals. Okay, total. So if I look at what's the probability that x is equal to 2, what I can do is I could just add the probabilities. So fix x equal to 2 and add up all the probabilities for the y's, for y equal to 1, 3, and 5, right here. Okay. And if I add those together, right, keeping x be equal to 2, and then I'm summing up all my y values, right? Then I get 0.4. And I can do the same thing for this one. I can have letting x equal to 4, right? And then keeping x equal to 4 and then changing my y values to sum up my probabilities, I get 0.6. And that's going to be my first marginals. So 0.4, 0.6. Those are the marginal probabilities. So this is probability x equal to 0.4. Probability x equal to 4 is 0.6. And then I can do the same thing for my marginal probabilities for y alone. The probability that y is equal to 1, keep y fixed, and sum over all my x values. Okay, that gives me 0.25. Keeping y fixed at 3 and summing over all my x values, I get 0.5. And keeping y equal to 5 and summing over all my x values, I get 0.25. And I'm going to write that down. And notice that I get 1, total 1 for whenever I do it. So these are actually my marginal distributions in the corner. So now you can get an idea why they're called marginal distributions, because they're in the margins, right? They're in the margins of my table, on the ends of my table, on the margins of my table. And so let me rewrite them so that they have their own table for the marginal distributions here. So I can say x and g of x, okay? 2 and 4, x is 0.4 and 0.6. For g of x, I should say g of x is 0.4 and 0.6. And y, I have 1, 3, and 5. I have h of y. This is going to be 0.25, 0.5, and 0.25. Those are going to be my part A and B answers here. Okay, so those are my marginal distributions. So this is 0. Okay. All right. And then what does C ask for? C says, what's the probability x is equal to 2? Well, the probability x is equal to 2 is 0.4. We just found that out already. What's the probability y is less than 4? Well, we can look at our marginal probability, right? And the y is less than 4. The probability of that occurring is going to be these two values here, which is going to be 0.75. Okay, 0.75. Now, I got those directly from the marginal distribution, but I also could have got the answer from looking at my joint probability distribution. If I go back, I could say x equal to 2. Just look at these values, add them together. This is where x is equal to 2. I would have got 0.4. Okay. Y is less than 4. I would need to look at every situation where y is less than 4, which are going to be these values, right? And these are going to be my probabilities right here where y is less than 4. And that would have given me also 0.75. So that's two ways I could have done it. I could have done it directly from the joint distribution or from the marginal distributions that I have here. And it's a little bit easier, I think, to work from the marginal distributions when you're looking for a probability of a single thing occurring, so a single variable, instead of looking at all of the variables together. Okay. We could also do this for a continuous function, and then we'll take a break and make sure that everything is recording well this time. When I did this actually yesterday, I recorded a lesson for you guys over the same material, and the computer lost all of the lessons. So this is my, I think, third time teaching the same lesson. So hopefully it'll stick this time. We'll see. All right. So it says this, we'll call this a fast food example. A fast food restaurant operates both a drive-through facility and a walk-in facility. On a randomly selected day, let X and Y respectively be the proportions of the times that the drive-through and walk-in facilities are in use. And suppose that the joint density function of these random variables is given by f of x, y is equal to, we have 2/3 x plus 2y. And x goes from 0 to 1. Y also goes from 0 to 1. Okay. 0 elsewhere. Again, my handwriting is terrible, so if hopefully you're listening to me talk and at the same time as I'm writing this stuff down so that you get the right things written down. Also, make sure you're looking at the PowerPoints as well at the same time that we're talking. And want to find the marginal density of x. Okay, find the marginal density of x. So g of x. Here I'm going to be integrating over my over all my y's, right? So that goes from 0 to 1. Okay, so that's going to be my limits for y of 2/3 x plus 2y dy. And that's going to be equal to, we have 2/3 x, 2/3 times the quantity x plus 1, where x goes from 0 to 1, and it's its own distribution. Okay, this is our answer for this one. And then the marginal density of y, h of y, integrate over all the x's now. X goes from 0 to 1. That's the limits for x. And when you do that, you get 1/3 times the quantity 4y plus 1. Y goes from 0 to 1. Okay. All right. Very good. And then C says, find the probability that the drive-through facility is busy less than 1/2 of the time. Busy less than 1/2 of the time. So if you look at this example, X represents your drive-through times, and Y represents your walk-in times. So we were looking at the probability that X is less than 1/2. So integrating over our region, so we integrate. I can use my marginal distribution here, so I can integrate from 0 to 1/2. 1/2. Okay, of my marginal distribution for x, which is 2/3 x plus 1 dx. And that gives me, I have 5/12. 5/12 is my answer. Now, I could have also done this problem a different way by using my joint distribution directly. And I could have done this double integral over my joint. Okay. And here I'm going to do dy dx, or I could do dx dy, it doesn't matter. Okay. And here I want to integrate over all the y's, right? Because they don't tell me what the y's are, so I'm assuming I'm going to have to integrate over all the y's that I can. But x is restricted from 0 to 1/2. Okay. And I get exactly the same thing, which is 5/12. The reason why is because the inner part, right? This inner part right here is just my marginal distribution that I calculated before. Okay. Just my inner distribution that I calculated before right here, this guy right here. Okay, and then I'm just integrating the outer part, which is this thing right here. I hope that kind of makes a little bit of sense. But we'll stop right there, and we'll pick up again with conditional distribution.